Hey, I'm Dr. Charles P. Winston, Young Elders Butler, a regularly featured guest on the Young Elders channel about extraterrestrials. I have years of research into the ancient astronauts and ancient technology from your distant past and future. Over 30 ancient cultures reference interaction with physical beings they considered to be gods. Modern archaeology considers these stories to be myth. We will be exploring the 9 states of existence in this amazing video. We encounter matter in our daily lives. It makes up everything around us. But matter is far more diverse and stranger than our everyday experiences suggest. Beyond the familiar solids, liquids, and gases lies a world of exotic states. These states exist under extreme conditions. They possess remarkable properties that defy our intuition. This exploration will take us on a journey through these fascinating states of matter. We'll delve into their unique characteristics and the conditions that bring them about. From the frigid realm of Bose-Einstein condensates to the scorching heat of quark-gluon plasma, prepare to have your mind blown by the wonders of the quantum world. Our journey begins with the familiar solids, liquids, and gases. These fundamental states form the bedrock of our understanding of matter, but even they hold surprises when we delve deeper. Get ready to see the familiar in a whole new light. And then we'll push beyond the familiar, venturing into the truly exotic. Fasten your seatbelts. We're about to embark on an incredible adventure through the diverse and fascinating world of matter. Let's start with what we know. Matter, the substance that makes up everything around us, exists in different states. These states are primarily determined by the arrangement and energy of the molecules that compose the matter. A state is a particular condition that someone or something is in at a specific time. The state a given substance exhibits is also a physical property. The state of a substance depends on the balance between the kinetic energy of the individual particles, molecules or atoms, and the intermolecular forces. Every molecule, every atom which builds up the cell of the physical body, is built around a center of light, which is the spiritual force. This is also the microverse, the smallest things, which you need a microscope to see. What are atoms? Atoms are the basic unit of a chemical element. An atom is the smallest unit of ordinary matter that forms a chemical element. Every solid, liquid, gas, and plasma are composed of neutral or ionized atoms. Atoms are extremely small, typically around 100 picometers across the microworld. The components of an atom are electrons and a compact nucleus of protons and neutrons. Each of these parts has an associated charge, with protons carrying a positive charge, electrons having a negative charge, and neutrons possessing no net charge or neutral. These are also called subatomic and hyperatomic particles, which are smaller than atoms. Quarks make up protons and neutrons, which in turn make up an atom's nucleus. Each proton and each neutron contains 3 quarks. A quark is a fast-moving point of energy. These 3 quark types are now commonly designated as up, U, down, D, and around, which they call strange matter, U channel to one point, which is 0-point energy. Once you break these things down, they are also called the biaps and Z's, Zeeles. These are subatomic particles. Once you speed up the vibrational frequency, past the biaps and Z's, you go into hypertonic particles, which are pions. It is this infinite small light dot, divine in aspect, life of light from Anu, El the Most High, the highest, which is the secret power that holds together the atom and molecules. It is the center of the molecular solar system. The atom is nothing more than a tiny solar system charged with electric and magnetic power. The atmosphere around you is completely charged with positive and negative beings from the microverse. The pions are lighter than the quarks. 2 pions make up a quarks, which makes up a biaps, meaning 2 APs, pions and antipions. Pions and plus pions make up a quarks. The pions are the most numerous pieces in the game of life, and in most circumstances it is thought of as the weakest, but the pion, being the smallest thing, pack a lot of power. The pions vibrate on the 0 point. They are what charge and heal your body when you are asleep. They are also called omega molecules, which are highly unstable molecules and the most powerful substance known to exist. The 9 states of matter commonly discussed are solid, liquid, gas, plasma, Bose-Einstein condensate, fermionic condensate, superfluid, quark-gluon plasma, and quantum spin liquid, with the first four considered the fundamental states of matter. Solids, like rocks and ice, hold their shape. They are rigid and have a definite volume. Their molecules are tightly packed, vibrating in place. This close arrangement gives solids their firmness and resistance to change in shape or volume. Liquids like water and oil flow and take the shape of their container. Unlike solids, they do not have a fixed shape but maintain a constant volume. Their molecules are more loosely arranged, moving around each other. This allows liquids to flow and adapt to the shape of their surroundings while still maintaining a consistent volume. Gases like air and steam have no fixed shape or volume. They expand to fill any container they are in. Their molecules are far apart, moving freely and colliding with each other. This high-energy state allows gases to spread out and fill any available space. These three states are governed by temperature and pressure. By changing these conditions, we can transform matter from one state to another. Heat things up, and they transition from solid to liquid to gas. For example, ice melts into water and water boils into steam. Cool them down, and the process reverses. Steam condenses into water and water freezes into ice. But there's a fourth state, often overlooked but incredibly common in the universe: plasma. Plasma is not as familiar to us in our daily lives, but it is the most abundant state of matter in the universe. Gas is a state of matter that has no fixed shape and no fixed volume. Gases have lower density than other states of matter, such as solids and liquids. When more gas particles enter a container, there is less space for the particles to spread out, and they become compressed as in compressed gas. In gas, there is a great deal of empty space between particles, which have a lot of kinetic energy. The particles move very fast and collide into one another, causing them to diffuse or spread out until they are evenly distributed throughout the volume of the container. The particles exert more force on the interior volume of the container. This force is called pressure. There are several units used to express pressure. Some of the most common are atmospheres, ATM, pounds per square inch, PESI. Gases are very sensitive to temperatures and pressure. Gas is already vibrating at a high speed, so some gases are very flammable. Acetylene, hydrogen, propane, propylene and methane are all flammable gases referred to as fuel gases. When these gases are mixed with an oxidant and provided with an ignition source, they will burn. A verb come in three tenses: past, present and future. What is time? Time is the measured or measurable period during which an action, process or condition exists or continues, duration. A continuum that is measured in terms of events which succeed one another from past through present to future. Time is based on light and distances and speed of object in that light. In different worlds, planets and galaxies, the time can change. It can be 1 day for 1,000 years. It could be 1 billion years for 1 day. It could be 365 billion years for 1 year. Once you vibrate faster than light, you move outside of what they're calling time. The concept of past, present and future is a product of time. The past is used to describe things that have already happened, meaning earlier in the day, yesterday, last week, 3 years ago. The present is used to describe things that are happening right now, or things that are continuous. The future describes things that have yet to happen, meaning later tomorrow, next week, next year, 3 years from now. The past plus present equal sign. The future. So it is a math problem. What happened in the past, added to what happened now, tell the future. This is what psychic power really is. They are really great at math. The total amount of energy and matter in the universe remains constant, merely changing from one form to another. As stated by Tahuti, energy is always conserved. It cannot be created or destroyed. In essence, energy can be converted from one form into another. Energy is the quantitative property that must be transferred to an object in order to perform work on or to heat the object. A liquid is a nearly incompressible fluid that conforms to the shape of its container, but retains a nearly constant volume independent of pressure. It is one of the four fundamental states of matter, the others being solid, gas and plasma, and is the only state with a definite volume but no fixed shape. The density of a liquid is usually close to that of a solid and much higher than that of a gas. Therefore, liquid and solid are both termed condensed matter. On the other hand, as liquids and gases share the ability to flow, they are both called Fluids. A liquid is made up of tiny, vibrating particles of matter, such as atoms, held together by intermolecular bonds. Like a gas, a liquid is able to flow and take the shape of a container. Unlike a gas, a liquid maintains a fairly constant density and does not disperse to fill every space of a container. Although liquid water is abundant on Earth, this state of matter is actually the least common in the known universe because liquids require a relatively narrow temperature-pressure range to exist. Most known matter in the universe is either gas, as interstellar clouds, or plasma, as stars. Liquid is one of the four primary states of matter, with the others being solid, gas, and plasma. A liquid is a fluid. Unlike a solid, the molecules in a liquid have a much greater freedom to move. The forces that bind the molecules together in a solid are only temporary in a liquid, allowing a liquid to flow, while a solid remains rigid. A liquid, like a gas, displays the properties of a fluid. A liquid can flow, assume the shape of a container, and, if placed in a sealed container, will distribute applied pressure evenly to every surface in the container. If liquid is placed in a bag, it can be squeezed into any shape. Unlike a gas, a liquid is nearly incompressible, meaning that it occupies nearly a constant volume over a wide range of pressures. It does not generally expand to fill available space in a container, but forms its own surface, and it may not always mix readily with another liquid. These properties make a liquid suitable for applications such as hydraulics. Liquid particles are bound firmly, but not rigidly. They are able to move around one another freely, resulting in a limited degree of particle mobility. As the temperature increases, the increased vibrations of the molecules causes distances between the molecules to increase. When a liquid reaches its boiling point, the cohesive forces that bind the molecules closely together break, and the liquid changes to its gaseous state unless superheating occurs. If the temperature is decreased, the distances between the molecules become smaller. When the liquid reaches its freezing point, the molecules will usually lock into a very specific order, called crystallizing, and the bonds between them become more rigid, changing the liquid into its solid state, unless supercooling occurs. Solids are divided into two main categories: crystalline solids and amorphous solids, based on how the particles are arranged. Crystalline solids, or crystals, are regarded as true solids. Minerals are crystalline solids. Common table salt is one example of this kind of solid. In amorphous solids, literally solids without form, the particles do not have a repeating lattice pattern. They are also called pseudo-solids. Examples of amorphous solids include rubber, gels, and most plastics. Liquid has a definite volume but take the shape of the container. Liquids are more dense and less compressible than gases. Liquids take water, for example, which is H20. Water is an inorganic, transparent, tasteless, odorless, and nearly colorless chemical substance, which is the main substance of Earth's hydrosphere and the fluids of all known living organisms on Earth. Water can take many forms. At low temperatures, below 32 degrees Fahrenheit or 0 degrees Celsius, it is a solid. When at normal temperatures between 32 degrees Fahrenheit or 0 degrees Celsius and 212 degrees Fahrenheit or 100 degrees Celsius, it is a liquid. While at temperatures above 212 degrees Fahrenheit or 100 degrees Celsius, water is a gas, steam, boiling. The state the water is in depends upon the temperature, so the state depends on the speed of the molecules based on temperature. This is also dealing with the dimensions. The slower the vibrating of an object, the colder the temperature, the faster the hotter the temperature. A familiar liquid is mercury metal. Mercury is an anomaly. It is the only metal they know of that is liquid at room temperature. Mercury also has an ability to stick to itself, surface tension, a property all liquids exhibit. Mercury has a relatively high surface tension, which makes it very unique. You see mercury in its common liquid form. If we were to cool liquid mercury to its freezing point of 39 degrees C, and under the right pressure conditions, we would notice all of the liquid particles would go into the solid state. Mercury can be solidified when its temperature is brought to its freezing point. However, when returned to room temperature conditions, mercury does not exist in solid state for long and returns back to its more common liquid form. Some substances have higher or lower boiling and freezing points. The gas is one of the four fundamental states of matter. A pure gas may be made up of individual atoms, elemental molecules made from one type of atom, or compound molecules made from a variety of atoms. A gas mixture, such as air, contains a variety of pure gases. Gas is one of the three fundamental states of matter. H20, which is water, contains 2 hydrogen atoms and 1 oxygen atom. Plasma is a gas that carries an electrical charge. It is created when a gas is energized to the point that its atoms lose electrons, resulting in a soup of charged particles. It forms when atoms in a gas are heated to such high temperatures that their electrons are stripped away, creating a sea of ions and electrons. This ionization process gives plasma its unique properties. Plasma is found in lightning, stars, and fluorescent lights. These examples show how plasma can be both naturally occurring and man-made. It's a fascinating state of matter with unique properties, like its ability to conduct electricity and interact with magnetic fields. These properties make plasma essential in many technological applications, from neon signs to plasma TVs. These four states, solid, liquid, gas, and plasma, represent the fundamental ways matter typically exists in our universe. Each state has distinct characteristics and behaviors that are crucial to understanding the physical world, but the story doesn't end there. Beyond these common states, there are even more exotic forms of matter that challenge our understanding of physics. Let's delve deeper into the quantum world and explore the more exotic states of matter. These include Bose-Einstein condensates, fermionic condensates, and other states that exist under extreme conditions. These exotic states open up new frontiers in science and technology, offering insights into the fundamental nature of the universe. Keep in mind that there are two sides to the mirror. We are on the negative side of the mirror, which is why when they take a picture, they keep the negative frame. You have zero, which is the center point, as in 0-point energy. Then if you go to the right, you get +1, and when you go to the left, you get -1. We are on the left, because the picture that produced more frames is on -1. Matter typically exists in one of three states: solid, liquid, or gas. Matter is the stuff of the universe, the atoms, molecules, and ions that make up all physical substances. Some substances exist as gases at room temperature, oxygen and carbon dioxide, while others, like water and mercury metal, exist as liquids. Most metals exist as solids at room temperature. All substances can exist in any of these three states. Solids have a definite shape and volume. In a solid, molecules are packed together, and it keeps its shape. They are not free to move about within the substance. Molecular motion of the particles in a solid is confined to very slow vibrations of the atoms around their fixed positions. Therefore, solids have a fixed shape that is difficult to change, without speeding up the vibrating by heating it up. In a solid, the molecules heat up and vibrate faster, they spread out and become liquid. The kinetic energy keeps the molecules apart and moving around, and is a function of the temperature of the substance. Heating and cooling can change the kinetic energy of the particles in a substance, and so we can change the physical state of a substance by heating or cooling it. This is alchemy in basis form. Increasing the pressure on a substance forces the molecules closer together, which increases the strength of intermolecular forces. Cooling a gas may change the state to a liquid. Cooling a liquid may change the state to a solid. Increasing the pressure on a liquid may change the state to a solid. The intermolecular forces are attractive forces that try to draw the particles together. A colloid is a mixture in which one substance, consisting of microscopically dispersed insoluble particles, is suspended throughout another substance. Some definitions specify that the particles must be dispersed in a liquid, while others extend the definition to include substances like aerosols and gels. The term colloidal suspension refers unambiguously to the overall mixture, although a narrower sense of the word suspension is distinguished from colloids by larger particle size. A colloid has a dispersed phase, the suspended particles, and a continuous phase, the medium of suspension. The dispersed phase particles have a diameter of approximately 1 nanometer to 1 micrometer. Some colloids are translucent because of the Tyndall effect, which is the scattering of light by particles in the colloid. Other colloids may be opaque or have a slight color. Alloy, metallic substance composed of two or more elements, as either a compound or a solution. The components of alloys are ordinarily themselves metals, though carbon, a nonmetal, is an essential constituent of steel. Alloys are usually produced by melting the mixture of ingredients. A chemical substance is a unique form of matter with constant chemical composition and characteristic properties. Chemical substances may take the form of a single element or chemical compounds. If two or more chemical substances can be combined without reacting, they may form a chemical mixture. Viscosity is the resistance of a fluid, liquid or gas to a change in shape or movement of neighboring portions relative to one another. Viscosity denotes opposition to flow. Viscosity is a measure of a fluid's rate-dependent resistance to a change in shape or to movement of its neighboring portions relative to one another. For liquids, it corresponds to the informal concept of thickness. For example, syrup has a higher viscosity than water. Chemical reaction, a process in which one or more substances, the reactants, are converted to one or more different substances, the products. Substances are either chemical elements or compounds. A chemical reaction rearranges the constituent atoms of the reactants to create different substances as products. A chemical bond is the association of atoms or ions to form molecules, crystals, and other structures. The bond may result from the electrostatic force between oppositely charged ions, as in ionic bonds, or through the sharing of electrons, as in covalent bonds, or some combination of these effects. Chromatography is a process for separating components of a mixture. To get the process started, the mixture is dissolved in a substance called the mobile phase, which carries it through a second substance called the stationary phase. In chemical analysis, chromatography is a laboratory technique for the separation of a mixture into its components. The mixture is dissolved in a fluid solvent called the mobile phase, which carries it through a system on which a material called the stationary phase is fixed. A polymer is any of a class of natural or synthetic substances composed of very large molecules called macromolecules, which are multiples of simpler chemical units called monomers. Polymers make up many of the materials in living organisms and are the basis of many minerals and man-made materials. Biochemistry is the study of the chemicals and chemistry of living organisms. Biochemists study biomolecules such as proteins, RNA, DNA, sugars and lipids, their applications and interactions in the body, and biochemical and metabolic processes. Chemical equilibrium, condition in the course of a reversible chemical reaction in which no net change in the amounts of reactants and products occurs. A reversible chemical reaction is one in which the products, as soon as they are formed, react to produce the original reactants. Electrochemistry is the branch of physical chemistry concerned with the relationship between electrical potential difference and identifiable chemical change. Chemical kinetics refers to the description of the rate at which a chemical reaction takes place, specifically the transformation of reactants into products. It focuses on the dynamics and thermodynamics of chemical reactions, addressing the change in concentration of contaminants over time. Thermochemistry is the study of the heat energy which is associated with chemical reactions and/or phase changes such as melting and boiling. A reaction may release or absorb energy, and a phase change may do the same. In the early 20th century, two brilliant minds, Satyendra Nath Bose and Albert Einstein, predicted a bizarre and fascinating state of matter that would challenge our understanding of the physical world. They theorized that at extremely low temperatures, close to absolute zero, minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit, a group of atoms could lose their individual identities and behave as a single entity. This was a revolutionary idea, suggesting that, under such extreme conditions, the rules of classical physics would give way to the strange and wonderful laws of quantum mechanics. This state of matter is called a Bose-Einstein condensate, or BC. In this state, atoms coalesce into a single quantum entity, behaving as if they are one giant atom. This phenomenon is not just a theoretical curiosity, but a profound insight into the nature of matter and energy. Imagine a group of individuals suddenly merging into a single superorganism, acting in perfect unison. This analogy helps us grasp the extraordinary nature of a BEC, where individual atoms lose their distinctiveness and move in harmony as a single, unified wave. That's essentially what happens in a BC. The atoms, once separate and distinct, come together to form a single, coherent quantum state. This collective behavior is a hallmark of quantum mechanics, where particles can exhibit properties that are impossible in the classical world. The atoms, cooled to near absolute zero, lose their individual energy states and occupy the lowest possible energy level, essentially becoming a single wave-like entity. This wave-like nature is a direct consequence of the quantum mechanical principle that particles can also behave as waves. Creating a BC in the lab was a monumental achievement, finally achieved in 1995 using lasers and magnetic fields to cool rubidium atoms. This breakthrough was a testament to human ingenuity and the relentless pursuit of knowledge, opening up new frontiers in the study of quantum mechanics. This breakthrough opened up new avenues in physics, allowing scientists to study quantum phenomena on a macroscopic scale. For the first time, researchers could observe and manipulate quantum effects in a controlled laboratory setting, leading to a deeper understanding of the fundamental principles that govern our universe. BCs behave like superatoms, exhibiting strange quantum properties like superfluidity and interference patterns. Superfluidity, for instance, allows the condensate to flow without any viscosity, defying our everyday experiences with liquids and gases. But the strangeness of the quantum world doesn't stop there. The study of BCs has revealed a plethora of other exotic behaviors and properties, each more intriguing than the last. These discoveries continue to challenge our understanding and push the boundaries of what we thought was possible. Let's move on to another fascinating state, fermionic condensates. These states of matter, predicted and observed under similar extreme conditions, offer yet another glimpse into the mysterious and captivating world of quantum mechanics. Fermionic condensates are like the rebellious cousins of Bose-Einstein condensates. While Bose-Einstein condensates are formed by bosons, which are particles that can share the same quantum state, fermionic condensates involve fermions, which are particles that cannot share the same state due to the Pauli exclusion principle. They also involve atoms behaving collectively at ultra-low temperatures, but with a crucial difference. In a Bose-Einstein condensate, bosons clump together in the same state, but fermions, like electrons and protons, need a different approach. Fermions, like electrons and protons, obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state simultaneously. This principle is fundamental to the structure of matter and the behavior of particles at the quantum level. So, how do you create a condensate of particles that refuse to share the same state? The answer lies in the fascinating world of quantum mechanics and the clever techniques developed by physicists. The trick lies in pairing them up. By using carefully tuned magnetic fields and ultra-low temperatures, physicists can coax fermions into forming pairs that act like bosons. These pairs, known as Cooper pairs, can then behave collectively. By using carefully tuned magnetic fields and ultra-low temperatures, physicists can coax fermions into forming pairs that act like bosons. These pairs can then condense into a single quantum state, exhibiting superfluidity and other intriguing behaviors. These pairs can then condense into a single quantum state, exhibiting superfluidity and other intriguing behaviors. Superfluidity is a phase of matter where a fluid can flow without viscosity, meaning it can move without losing energy. The discovery of fermionic condensates in 2003 added another layer of complexity to our understanding of matter. It was a significant milestone that demonstrated the versatility and richness of quantum mechanics. It highlighted the subtle interplay between quantum statistics, interactions between particles, and the emergence of collective behavior in the quantum world. This discovery has opened up new avenues for research and potential applications in quantum computing and other advanced technologies. These condensates, both bosonic and fermionic, showcase the mind-boggling nature of matter at extremely low temperatures. They reveal the strange and wonderful behaviors that emerge when particles are cooled to near absolute zero. But the universe also offers extreme conditions at the opposite end of the temperature spectrum, leading to states like superfluids and quark-gluon plasma. These states occur at incredibly high temperatures and energies, providing a fascinating contrast to the ultra-cold world of condensates. The study of these extreme states of matter, both hot and cold, continues to push